Welcome to this model of source model for gases. In this, before we start this module, let us have a look at what we have studied in previous modules. We have gone through the difference between the handling of liquid and vapors. We have discussed various type of flow of vapor through hole and a pipe, and we model and we discussed the various models. Flow of vapors through holes. We have discussed about the flow of gases through pipes and their types. We have gone through the flashing of liquids. So, in this particular module, we are going to discuss about the liquid pool evaporation or boiling, pool evaporation of highly volatile liquids. These two phenomena are extremely important in chemical engineering process industries when we are handling the liquid system. So, in the introduction part, let us have a look at what is evaporation and a boiling. So, evaporation occurs at the liquid vapor interface when the vapor pressure is less than the saturation pressure of the liquid at a given temperature. Whereas boiling, this occurs at the solid liquid interface when a liquid is brought into contact with a surface mentioned at a temperature sufficiently above the saturation temperature of the liquid. So, this is the basic difference between the evaporation and a boiling. So, whenever we are considering the boiling, boiling is divided into different categories like pool boiling, flow boiling. So, pool boiling, this is the boiling in the absence of bulk fluid flow and motion only due to the boiling factors. So, this is related to the pool boiling. When we consider the flow boiling, the boiling is in the presence of bulk fluid flow and the fluid is forced to move in a heated pipe or over a surface by external means such as pump. Another aspect is the subcooled boiling. So, usually occurs when a temperature of a main body of the liquid is below the saturation temperature. Saturated boiling, when the temperature of the liquid is equal to the saturation temperature of the liquid in question. So, this is the difference between the subcooled boiling and a saturated boiling. So, pool boiling usually is a phenomena in which vapor is generated at the surface of a superheated wall whose surface is dimensionally small as compared to the surrounding liquid, that is pool, in which it is submerged. So, the motion of the liquid towards the heating surface is induced by the boiling process. Now, the liquid at higher temperature have the lower density compared to the adjacent liquid at the lower temperature. So, this is the governing equation for that particular segment. Now, the motion of the vapor away from the heating surface will be induced by the buoyancy effect of the vapor. So, the velocity of the motion for both phases is assumed low. Now, bubbles usually do not form on heating surface until the liquid is heated a few degrees above the saturation temperature. Now, this particular state is referred as metastable state and the liquid is slightly superheated in that particular case. Now, heat transfer from heating surface to the fluid by the natural convection. So, usually this occurs by the natural convection. There are certain important industrial perspectives. Now, pool boiling is unusual in industrial instruments as multiple heating devices are used in single pool. Now, if a flow of liquid past the wall of the heating mantle may be considered zero, then also due to the confinement of the liquid and due to the presence of multiple heaters, the behavior will be considered close to the forced convective boiling. You can have a look in this particular diagram. There are this is a typical heat exchanger, steam, condensate, bottom product, liquid fuel, and the boiling. Here is the phenomena of pool boiling. Now, however, the special conditions usually implemented in the pool boiling experiments such as the maximum possible flow rate of vapor and a liquid away and towards the heating surface respectively, that is called the critical heat flux, and the no force convection of liquid or vapor. So, provided this provides a very important information for designing the large scale industrial system. Now, the peak heat flux or Bernoulli heat flux represents the upper limit of fully developed nucleate boiling. You can have a look this in this particular, this is the nucleate boiling zone, this one. So, while designing the engineering component, this heat flux provides the maximum limit of safe operation. Beyond this limit, the heat removal rate from the surface of heating device degrade substantially, and this leads the melting or burnout of the surface. So, usual question arises that how this pool boiling occur. Now, liquid is in contact with the surface maintained at a temperature above the saturation temperature of the liquid. So, boiling occurs at the liquid solid interface, that is the thin boundary between the outer surface of the hot element and the adjacent film of liquid from the surface. Now, one thing to be noted that based on the contact between the liquid and a heating surface, liquid boiling is divided into two categories. One is pool boiling and second is the convective boiling. Now, sometimes you need to draw the boiling curve. So, let the liquid is heating using the cylindrical wire submerged horizontally under the water level. Now, if we plot the graph between the heat flux and the temperature, we get a boiling curve. Now, this curve is between the heat flux and temperature. Now, this curve can be divided into 6 regions, which is represented here. Region 1, the pure convection, superheated liquid rising to the interface. This is the nucleate boiling with bubbles continued in the liquid. This one is the nucleate boiling with the bubble rise to surface. This is the partial nucleate boiling and unstable film boil. This is the film boiling is stabilized under this fifth zone, and the last zone is the radiation becomes the dominant in this region. So, let us have an elaborative approach of this particular plot. Now, let us consider this region 1. This region 1, temperature difference between the surface and stagnant liquid layer very small, hence the vapor form only due to the evaporation of the liquid into gas nuclei over the exposed surface of the liquid. You can have a look of this particular region. Now, second region, that is the nucleate boiling, this one. Now, with increase the temperature difference, additional small bubble form along the heating surface, but later condense in the region above the superheated liquid. In the third region, that is bubble rise to the surface, this one, the bubbles rise to the surface. The temperature difference is strong enough to sustain nucleate boiling. Bubbles start leaving the surface irrespective of the condensation rate. Now, in the fourth region, this one is the fourth region. Now, that is the unstable film boiling. An unstable film of vapor forms over the heating surface, and the heat transfer rate decreases due to the presence of film over the surface. Now, the region 5 attributed to the stable film formation. Now, you can see in this particular, this is the region 5. The stable film of vapor form over the heating surface and heat transfer rate becomes minimum. The last region, that is the radiation heat transfer dominance region. In this particular, the radiation heat transfer dominates and temperature difference becomes so strong, also stable film formation reduces the convective heat transfer rate. Hence, the radiation heat transfer becomes dominating phenomena in this particular region. You can have a look in this particular curve. So, this is all the 6 regions of this particular phenomena. Now, next is your pool evaporation of highly volatile liquids. This particular phenomena is extremely common in process industry. Now, for this, the calculation of mass vaporization rate is carried out. So, the total mass flow rate of evaporation of a volatile from the pool of a liquid, this is determined by this equation. Earlier in a different module, we have derived this particular equation. Qm is equal to mkap saturation R upon RTL. Qm is the mass vaporization rate, that is the unit of mass per time. M is the molecular weight of the pure material. K is the mass transfer coefficient having the unit of length per time. A is the area of exposure. P saturation is the saturation vapor pressure of the liquid, and R is the ideal gas constant, and T is the temperature of the liquid. So, in case of volatile liquid heating from the surrounding, the boiling phenomena is limited to heat transfer from the surrounding to the liquid. So, different modes of heat transfer, while considering if this aspect, then heat is transferred from the ground by the convection. Usual equation applicable is Q is equal to Ka T2 minus T1 upon L. Now, from air by conduction and convection, Q is equal to Ha T2 minus T1. By radiation from the sun and adjacent sources such as fire, etc., then Q is equal to epsilon small sigma A T2 to the power 4 minus T1 to the power 4. Now, this is the Stephens-Boltzmann constant having the value of 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Epsilon is the emissivity of a surface value, and usually value is ranging from 0 to 1. Now, for liquid having the boiling point below ambient temperature, boiling is controlled initially by heat transfer from the ground and due to the conduction from the heated ground. Now, the heat transfer from ground is modeled with a simple one-dimensional heat conduction equation, that is Qg is equal to Ks Tg minus T upon pi alpha s T to the power 1 by 2. This equation is not considered conservative. Now, here Qs is the heat flux from the ground energy having the unit of energy per area time. Ks is the thermal conductivity of the soil energy per unit length time and degree. Tg is the temperature of the soil in degree, this one. T is the temperature of the liquid pool in degree, this one. Alpha S is the thermal diffusivity of the soil having the unit of area per unit time, and small t is the time after spill, that is the unit of time, this one. So, the rate of boiling is determined by assuming that all the heat is used to boil the liquid, that is thus. So, Qm is equal to Qg A upon delta Hv. Qm is the mass boiling rate, Qs is this one, S is the heat transfer for the pool from the ground, A is the area of the pool, and delta Hv is the heat of vaporization of the liquid in the pool, that is energy per unit mass. So, solar heat fluxes and convective heat transfer from atmosphere become important when the temperature difference between the ground and the boiling liquid becomes small. For spillage of high volatile matters such as liquefied natural gas (LNG), these heat fluxes become more important and may be only contributors towards the evaporation of the liquid. The higher hydrocarbons, especially from C3 and above, require a more detailed heat transfer mechanism. Now, this model also neglects the possible water freezing effect in the ground, and which can significantly alter the heat transfer behavior. This is very important phenomena. Now, let us have a look of different heat sources. So, industrial plant usually provide heat transfer using very high temperature single phase fluids such as air, or a condensing fluid such as superheated steam. Now, this is true for the case of forced convective heat transfer, but for pool boiling it is practically not at all possible due to the difficulty possessed in measuring the wall temperature. Hence, electrically resistive heat transfer is used to conduct the process in controlled heat flux. So, let us have different heating methods. So, in method number 1, the heating can be done using cylindrical tubes or rectangular plate mold made from thin electrically conductive material or metal or alloy such as nichrome. The uniform heat input is calculated from the current and voltage across the reactor. the temperature measuring devices such as a thermocouple are attached to the surface of the wall which do not participate in the boiling process. Now this non-boiling surface is maintained adiabatic by thermal insulation or guard heating. Another method attributed, now as we know that electricity flows only through the surface of electrically conductive material and not inside the surface. So electrically conductive material such as gold or tin oxide is doped over the insulated material. Glass is used as a substrate to provide the optical transparency. Now temperature is measured from its electrical resistance or measured at the back of the substrate. A very thin layer is doped over the substrate. Then we can also observe the boiling process from the back side. The third method is the indirect electrical heating in conjunction with the thick wall of a good thermal conductor such as copper or aluminum. An electrically insulated element is embedded or clamped to the back of the wall. The thermocouples are installed in the wall to measure the temperature. Now this method can be used for heater of circular or rectangular cross section. Now let us have a look of burnout phenomena. A typical boiling process usually does not follow the boiling curve beyond this particular point, point number C. So when the power applied to the heated surface exceeded the value at point C, this one, even slightly, the surface temperature increased suddenly. Now you can see here to a point number E, this one. So when the power is reduced gradually starting from point this, the cooling follows a sudden drop in the excess temperature when the point D is reached, this point. So, now let us have a look of heat transfer correlation in pool boiling. Now different heat transfer relations need to be used for different boiling regimes. In the natural convection boiling regime, heat transfer rates can be accurately determined using the natural convection relations. Now let us have a look of the nucleate boiling region. There is no general theoretical relations for heat transfer in the nucleate boiling regime. Experimental based correlations are sometimes used. The rate of heat transfer strongly depend on the nature of nucleation and the type and the condition of the heated surface. A widely used correlation proposed by Renshaw in 1952 is given by this particular equation. Qs is equal to mu1 hfg, then g rho 1 minus rho v upon small sigma to the power half, then Cpl delta T E upon C SF HFG Prandtl number to the power n, the entire whole Q. Now here Q dot is the nucleate boiling heat flux, this one. Mu1 is the viscosity of the liquid in kilogram per meter second. G is the gravitational constant. Rho 1 is the density of the liquid and rho v is the density of the liquid. CSF is the experimental constant which depends on surface fluid combination, this one. The surface tension of the liquid vapor interface is this one. Then CPL, that is the specific heat of the liquid in joule per kilogram degree Celsius, this one. TS is the surface temperature of the heater. T saturation is the saturation temperature of the fluid in degree Celsius. PRL is the Prandtl number of the liquid. N is the experimentation constant that depends on the fluid. So for nucleate boiling region, the value of Rosenhau equation can be used for any geometry, since it is found that the rate of heat transfer during the nucleate boiling is essentially independent of the geometry and orientation of the heated surface. The correlation is applicable to clean and relatively smooth surfaces. Error for heat transfer rate is given excess temperature, that is 100%. Error for the excess temperature for a given heat transfer rate for the heat transfer rate and by 30%. The critical heat flux, the maximum or critical heat flux in nucleate boiling was determined theoretically by SS Kotatelej in Russia way back in 1948, and N. Zubair in the US in 1958. So it is represented by this particular equation where Q dot maximum is equal to CHFG rho V small sigma G rho L minus rho V upon rho V square to the power quarter 1 by 4. Now here C is the constant whose value depends on the heater geometry, but generally is about 0.15. Now this CHF, that is the critical heat flux, is independent of the fluid heating surface combination as well as the viscosity, thermal conductivity and the specific heat of the liquid. This CHF increases with the pressure up to about 1/3 of the critical pressure and then starts to decrease and becomes 0 at the critical pressure. The CHF is proportional to HFG and a large maximum heat fluxes can be obtained using the fluid with a large enthalpy of vaporization such as water. The minimum heat flux which occurs at the Leidenfrost point is of the practical interest since it represents the lower limit of heat flux in the film boiling region. Now Zubair derived this particular expression for the minimum heat flux for a large horizontal plate, and this relation can be given by 50% or more. In this particular module, we have discussed the pool boiling, various aspects of pool boiling and a modeling aspect of pool boiling. And in case of any query or a you can always feel free to see these references. We have listed 12 references for the future study. Thank you very much.